Greetings and welcome to the Chemistry 222 Calorimetry Lab, where we're going to look at heat transfer and see how it applies specifically to chemistry. Along the way, we'll also look a little bit about the difference between a Q and a delta H, and we'll use Hess's law to figure out the delta H of formation for zinc oxide. So without further ado, let's get into this cool lab. Not really cool because it's about heat transfer. Ba-bum-bum. Sorry, couldn't resist. My humor is horrible. I apologize. Calorimetry is the study of heat transfer. That's why being cool is kind of silly, because heat is hot and it's being transferred, etc. Anyway, in calorimetry, people will use what's called, especially in these kind of labs, a coffee cup calorimeter. And a coffee cup calorimeter is nothing more than usually two coffee cups, like one inside the other, with some kind of a lid on it. And then the lid, if it's fancy, can have little holes in it, where a hole can be a thermometer or maybe even a stirrer. The lower right side shows the components of it. So inside you've got the reaction mixture, and you sometimes have some way to stir it with a thermometer to measure the temperature. On the left hand side is what a coffee cup calorimeter usually looks like. They're usually just some kind of cheesy coffee cups put together. The coffee cups are there because they're insulated, so you have a really good heat retention. It keeps outside heat sources out, stuff like that. In part A, we're going to use the calorimeter to find the specific heat of an unknown metal. All species in every phase have specific heats, which is how much energy it takes to raise 1 gram of the substance by 1 degree Celsius. Water's value of specific heat is 4.184 joules per gram Celsius, or joules per gram Kelvin. That says that 4.184 joules are required to raise 1 gram of water by 1 degree Celsius, or 1 Kelvin. The metals will have a specific heat value as well. So many joules required to raise 1 gram by 1 degree Celsius. And the goal is to figure out what that value is. In part B, we're going to use the calorimeter to find the heat of formation, which gets this fancy symbol delta H of little f right there. The F stands for formation for zinc oxide. And if you have a formation reaction, you only have 1 mole of product, and all reactants are elements in their standard states. So even though oxygen is a diatomic, even I, who hate fractions, has to use 1/2 right there, because we only want 1 oxygen in the ZNO. Delta H is the symbol for enthalpy, and enthalpy is a Q, a heat, but it's transferred at constant pressure. This is something we'll talk about more in lecture. But you can see how here, part A, the goal is to find specific heat. In part B, we're trying to find that delta HF value for zinc oxide. So in part A, in order to find the specific heat, we need to talk a little bit more about how this works. And the first law of thermodynamics, which is basically one of the big rules that all the physical sciences follow, says that energy can't be created or destroyed. Now, in chemistry, we usually focus on the heat, which gets the symbol Q. There is another type of energy called work, which gets the symbol W, and in physics, that becomes really important. But for chemists, it's mostly about the Q. So if energy can't be created or destroyed, which again is essentially heat, you can think about it as a hot piece and a cold piece coming together. You wouldn't make or destroy any energy. So you can write that as Q hot plus Q cold equals 0. That's the scientist's way of saying heat can't be created or destroyed. If you put one of the Q's on the other side, you end up with that Q hot equals negative Q cold, and that's the one we're going to use. And that comes again because you don't have any energy being created or destroyed. All the energy is conserved, and because we're talking about just heat Q, we can allow that to happen, and we'll see that used here in a little bit. So Q hot for us is going to represent a piece of hot metal. We're going to heat the metal in boiling water and transfer that hot metal to cold temperature, room temperature water. So Q cold is going to represent the room temperature water. So every time you see Q hot, think the metal. Every time you see Q cold, think the room temperature water we're going to start with. Now, hot and cold together always creates warm, something lower than the hot temperature, but higher than the cold temperature. And that temperature, that warm temperature, will be the same for both the hot metal and the cold water. They're going to transfer their heat to each other. The equation we're going to use in this particular part of the lab is Q equals mc delta T. M stands for the mass in grams of the object. C is that specific heat, all right, that we're going to be looking for. Specific heat is joules per gram Kelvin that I listed there, but it can also be joules per gram degrees Celsius. Either way is fine. And delta T is the change in temperature. Delta always means final minus initial in science. So this would be the temperature of the final solution minus the temperature of the initial solution. Now, remembering that the hot is the metal and the cold is the water. Q hot equals negative Q cold, you end up with this expression right here, where mc delta T represents the hot metal, and that equals negative Q cold. Q cold is mc delta T for water. And this is the equation we're going to use to find the C of metal, the heat capacity of the metal. So you can think about the goal of part A essentially as being able to find a good value for that C metal. You will use this equation later when you write up some of the data, so remember this in the back of your mind. Specific heat is a really interesting thing. Every substance has a specific heat, and liquid water, which is what most of the Chem 221 through Chem 220 series is all about, is 4.184 joules per gram Kelvin. And that can be listed in different ways. Sometimes it's joules, grams negative 1, Kelvin negative 1. This just means 1 over grams, 1 over Kelvin. So it's like joules over grams and kelvins. Sometimes you'll see it listed something like that, where they're both in the denominator. That's cool. And then finally, because a delta T is used, final minus initial, you can actually use Celsius or Kelvin. So you can see back going up to the top here, initially I had Kelvin, but then I said or degrees Celsius. The difference in Kelvin between two temperatures is the same as the difference in temperatures if they're in Celsius. And you can test this out yourself if you want, but it's pretty amazing. The difference between the boiling point of water and the freezing point of water in Celsius would be 100 to 0. So 100 minus 0, 100, okay. In Kelvin, it would be 373.15 and 273.15. So again, the difference between those is also 100. So when it comes to specific heats, you're going to see joules per gram Celsius and joules per gram Kelvin. They really are the same thing since it's a delta T, so FYI. I would usually use Celsius just because you wouldn't have to convert to Kelvin, but it's your call. Now again, all substances will have some kind of specific heat, and here's just some representative examples. So aluminum, lead, silver, etc., etc. There's water, 4.184. Notice how it says water as a liquid, water as a solid, i.e. ice, and water as a gas, i.e. steam, have different heat capacities than liquid water. So not only do you take into account the phase, you also have to take into type of material. Your goal is just to find the heat capacity of your unknown metal. Now in part B, we're going to use the idea created by Hess, and there's this little picture in the lower left. We're going to use several known equations to find the overall heat value, which is given the symbol delta HF, for this reaction right here. And it's zinc plus half an oxygen making zinc oxide. And that doesn't look that cool initially, but this is what they call a heat of formation reaction. A delta HF is a special kind of delta H. Remember, delta H is related to Q. It's essentially a heat at a constant pressure. You don't need to worry about that, but it's a type of a heat, all right? If you have a delta HF, that means two things. It means you have just 1 mole of product, so we only have 1 ZNO. It's not 2 or something like that. And it also means that all reactants are elements in their standard states. So we have zinc as a solid and oxygen as a gas. We wouldn't use like liquid zinc or solid oxygen, something weird like that. You have to use the normal version of the elements. And because there's only 1 mole of product, that's why sometimes we have to use fractions on these in order to make 1 mole and 1 mole only of products. In problem set number 5 of Chem 221 or at mhchem.org/thermo, there's a list of these delta HF values, and there's lots of things you can do. In lecture, we'll talk about delta H of products minus delta H of reactants. Those kind of delta H's are delta HF formation, so they're super, super helpful for scientists. We're going to try and find one of those delta HF values, the delta HF for zinc oxide. In order to find this value, we're going to use 2 other heat of reactions. One of them is going to be zinc and HCl, and the other one's going to be zinc oxide and HCl. Very exothermic reactions. We'll combine those 2 with the third delta HF equation for water, and using all that, we're going to be able to find the value for this delta HF for zinc oxide. And again, this is what uses Hess's law. Hess was pretty clever how he started using these ideas. We'll see how this all works out. So in part B, you're essentially going to do 2 experiments, zinc plus HCl and zinc oxide plus HCl. You'll measure a change in temperature, and they're both going to be exothermic, lots of energy given off. You can convert that to a delta H for each of those equations and combine that with a third equation to give our desired delta HF for the zinc oxide reaction right there. Hess's law is pretty cool, and you've probably seen this already, but I want to make sure everybody's up to speed. So I want to show an example of how Hess's law works. The first 2 equations right here are examples of combustion reactions, which is like a burning. And burning things is easy to do in the lab and maybe kind of fun too. But of course, I don't want to admit that as the chemistry instructor. Burn, burn. Anyway, Prophet back on. Anyway, those are both examples of combustion reactions. The first one is taking a compound called ethene, C2H4. You don't need to know that. Like all combustion reactions, you take something organic, you add O2 to it, and the only products are CO2 and water. And notice it has a very negative delta H. That means very exothermic, lots of energy given off. Now the second reaction is the C2H5OH. That compound is called ethanol, something else you don't have to worry about. It reacts with oxygen, and the only products are CO2 and water. Also very exothermic, very negative, lots and lots of energy given off. Now those 2 reactions are kind of easy to do because you're just burning something, and maybe kind of fun too, let's be honest. However, you can use those 2 equations to find the enthalpy, the delta H value, for this reaction. This is ethene plus water making ethanol. Now this would be a harder reaction to do, all right? It's not as much fun as just lighting a match on something. All right, and that can be kind of fun actually. But in this reaction, you're adding water to an organic compound to make the C2H5OH. That would be a harder, it's kind of slower, not as easy to tell if it was done reaction. However, using Hess's law, this isn't too bad. Now, in Hess's law, you can flip equations around. And as we talked about in lecture, if a reaction is exothermic in one direction, it will be endothermic in the opposite direction. So, for example, if we flip the C2H4 reaction around, C2H4 and 3 O2s would become products, and 2 CO2s and 2 waters would become reactants. If we do that, you change the sign. You change the sign of delta H. So what was an exothermic negative 1411.1, and that way, if we flipped it, would become a positive 1411.1 kilojoules. In this example, you don't want to flip the C2H4 reaction because in the desired reaction, which will give you a hint here as to what to do, C2H4 is a reactant, just like C2H4 was a reactant right there. So we want to leave that one alone. But if you look in the desired reaction, C2H5OH was a product. And in the second given reaction, C2H5OH was a reactant. So we certainly want to flip the second reaction around. And this part right here shows that. Notice how 2 CO2 and 3 H2O are now reactants. Up here they were products. And here's the C2H5 and 3O2 as products instead of reactants. And notice here in bold, a negative 1367 became a positive 1367.5. Now, why you want to do this is hopefully by adding these two equations together, it's going to give us the desired equation. You're always aiming to go after the desired equation in Hess's law, and that's what we want. And if you look here carefully, two CO2s that are products right there are canceled, if you will, by two CO2s, which are reactants. So if we subtracted two CO2s from both sides, like you would subtract 2x from math, you can cancel out the 2x on both sides. These two are going to cancel. And if you look at this carefully, 3 O2s as reactants there and 3 O2s as products right there, those are going to cancel out. So there shouldn't be any water, any CO2 or any oxygen. Not necessarily water though, I started to get too excited there. 2 waters are there and 3 waters are there. So these 2 waters will cancel all but 1 of the waters right there. So notice I haven't touched the C2H4. There's 1 water left over. And on the product side, the only thing left standing is C2H5OH. So combining those two equations together, we get the desired equation, C2H4 plus water making C2H5OH. The delta H for this reaction will be literally just the sum of these two numbers right there. So if you take negative 1411.1 and add 1367.5 to it, you get negative 43.6. That number is the delta H for C2H4 plus water making C2H5OH. And again, that's kind of cool because we use two equations which were really easy to do. Burning is an easy reaction to study. We combined them to give a delta H for a reaction which would be much harder to do. Adding water to something is sometimes hard to even know when it's done. So this is the power of Hess's law. It's really cool how it works out. Make sure that you change the sign of the part you flip. Maybe you need to flip both of them or one of them or none of them. It's hard to say, but this is a power you can do when it comes to Hess's law. So in this lab, the goal of part A is to find that specific heat of an unknown metal. You're going to heat an unknown metal in boiling water. You'll add that hot metal to some cold room temperature water. You'll mix it up a little bit. You look for the warmest temperature possible, so it'll go up a little bit, and that's what you'll do. In part B, the goal is to find the heat of formation of zinc oxide. You're going to do 2 reactions, zinc plus HCl, as well as zinc oxide plus HCl. You'll turn that data into a delta H and then use Hess's law to find the delta HF of zinc oxide. In a little bit here now, I'll show you a quick video which shows what you will do. You'll go through the calculations. If you do have any questions at any time, you by all means let me know. This stuff is all stuff you can do. It can be a little bit strange at first, so don't feel bad. And if you do have questions, email me, get some help. It's not a problem. Okay, at this point, I think it's time to watch a video to see how the lab is going to work when we actually get into the lab. This is kind of a fun lab. Definitely wear your goggles when you're dealing with a lot of these chemicals, especially the hydrochloric acid. It's pretty strong. Check this video out, and if you have any questions, let me know. Good luck on your lab.